Inside the math of a single definite energy state, the concept of a particle moving through space disappears. When Erwin Schrödinger formulated the equations of quantum mechanics, he established that electrons bound within an atom exist in allowed, locked-in energy levels. Physicists use the time-independent Schrödinger equation to identify these precise, unmoving energy states. In the infinite square well, a particle's ground state is a single eigenfunction. Though seemingly static in 2D, its real and imaginary parts spin in the complex plane over time. To find the observable probability density, we multiply this wave by its complex conjugate. This multiplication cancels the time-dependent phase factors, resolving to 1. Every trace of time dependence is erased from the observable result. This result explained why bound electrons don't constantly radiate energy and collapse into the nucleus. Because a definite energy state forms a stationary standing wave, the charge distribution does not move. However, if every allowed energy level is a stationary standing wave, we are left without a mathematical mechanism to explain a moving classical world. The time-independent equation is a special case, applicable only when the potential remains constant with time. The complete picture is found in the time-dependent Schrödinger equation. This equation includes a time derivative operator on the right side, which dictates how a quantum state evolves. Plugging a single stationary eigenstate into this time-dependent equation still yields a static probability density with zero physical motion. To generate an observable probability density that evolves over time, the system must occupy a linear combination of different energy states simultaneously. We construct this through a superposition state, a linear combination where two different stationary eigenstates exist at once. For this interference to result in movement, the two states must belong to different energy eigenvalues. This four-term expansion reveals the probability density for a two-state system. The first two terms represent the individual probabilities of state 1 and state 2. These terms independently cancel out their own time factors, remaining static baselines. The motion is encoded in the final two lines. These cross terms are created by the multiplication of the two different states. Because the states have different energy eigenvalues, their frequencies differ. When multiplied, the complex exponentials in these terms fail to cancel out. This surviving phase difference allows the probability density to fluctuate over time. Physicists simplify this complex conjugate pair by extracting the real part, resulting in this cosine equation. Taking the real part of this phase difference yields a pure oscillating cosine function. In the infinite square well, we start with these two unmoving baseline states. When we add the cosine cross term, its oscillation interacts with those baselines, driving the total probability density back and forth across the well. The frequency of this sloshing motion is directly proportional to the energy difference between the two states. Because this oscillation is rhythmic, the wave will periodically realign into its starting position, creating a grand recurrence. Physical motion at the quantum level is the result of this rhythmic sloshing, caused by perfectly stationary states interfering with one another. To see how this translates to a laboratory measurement, we calculate the expectation value of position. This calculation requires integrating the sloshing probability density over all space. The final line of the derivation reveals that the position integral splits into stationary terms and the single motion term. Because of the surviving cosine cross term, the particle's center of mass now explicitly depends on time. A shifting expectation value of position over time mathematically implies that the system possesses velocity. This time-dependent center of mass proves that quantum interference translates directly into macroscopic momentum. By combining dozens or hundreds of these individual stationary eigenstates together, we can construct a fully localized quantum wave packet. Ehrenfest's theorem ties this quantum wave packet to classical physics. The first equation shows the expectation value of position's rate of change is proportional to momentum. The second demonstrates this momentum change is determined by the potential's negative gradient. These quantum mechanical equations are structurally identical to Newton's laws of motion. When the environmental potential changes gradually compared to the wave packet, the packet's center perfectly traces a classical trajectory. Classical reality emerges as the macroscopic consequence of countless stationary quantum states interfering with one another.